Now, here's a term you are going to hear a lot in transport phenomena. Flux. I know, sounds like a sci-fi thing, right? But it's actually really simple. Think of a flux as the rate at which something flows through a surface. It could be heat, mass, or momentum. Imagine you are at a train station and people are passing through the gate. If 10 people walk through every second, that's a people flux through that gate. In transport phenomena, we replace people with stuff like heat, molecules, or momentum, and we measure how much of it moves through a certain area every second. Now, if you have got the image open, the one and the arrows, that's showing flux too. Picture this. You have got a wall and fluid is flowing past it. The arrows in the image, they represent the stuff, maybe heat or momentum, moving across a surface. The denser the arrows, the greater the flux. It's like more people pushing through the same gate at once. So whether it's heat flux, mass flux or momentum flux, they allow to follow the same idea. How much stuff is crossing a boundary and how fast? Once you understand this image, the idea of stuff flowing across a surface, you are already halfway into the heart of transport phenomena.
Muskan, imagine you are in a kitchen. One side smells like biryani, that other doesn't. You just know that smell is moving. That's a perfect real life example of molecular flux. It is a movement of molecule due to a difference in concentration. Technically, it's about molecules moving because of a driving force. Sounds fascinating, but super relatable, right?
Yeah, totally. So, molecular flux is like things moving naturally on their own. No fan, no stirrer, just vibes and signs. But then there's convective flux, where the movement is more aggressive. Like when you switch on an exhaust fan and all that steam rushes out. That's bulk flow.
Exactly. One side subtle, others like make way. Molecular flux is about potential gradients, like heat moving from hot to cold or perfume spreading. Convective flux, that's a bulk motion, like water flowing through a pipe or a wind carrying pollen through a garden.
It's kind of poetic, right? One's about natural, quiet shifts, the other's like, let's move people. And both of them are super important in understanding how stuff moves, whether it's heat or movement.
In this part, we are going to study about Newton's law of viscosity and momentum flux. Alright, ever tried dragging honey with a spoon? It resists, right? That sticky, slow pull. That's viscosity in action. And Newton, the guy who had an apple fall on his head, he gave us the law for it.
Yes, so Newton's law of viscosity says the shear stress between fluid layers is proportional to the velocity gradient, or in simpler words, how fast one layer is moving compared to the next.
You are right. Imagine two sliding glass plates with honey in between. The bottom is still, top one is moving. The honey layer in between, they stretch. And the faster the top plate moves, the more stress the fluid feels.
So the formula goes something like tau is equal to mu into dv by dy, where tau is a shear stress, mu is viscosity, and dv by dy is velocity gradient. It basically tells how much the fluid resists being deformed.
Absolutely, it is called the momentum flux because momentum is being transferred between the fluid layers like a pass the parcel, but the force and the motion.
Also, viscosity is a property that controls how fast or slow the parcel moves. Low viscosity like water, fast and chill. High viscosity like honey, slow and moody.
So in short, Newton gave us the relationship. Viscosity is the hero, Momentum flux is how motion spreads through a fluid. Visually understand viscosity. Imagine you are spreading butter between two slices of bread. You press one slice and slide the other. The butter in the middle, it stretches and resists. That's literally Newton's law of viscosity in action, but in sandwich form.
Oh, I like that. So if we look at the diagram, the bottom layer of the fluid is still. The top one moves with velocity v. Between them, there is a gradient. Layers in between move with spreads between 0 and v. That smooth change, it's called linear velocity profile.
Exactly, and that force you apply on the top layer, that is a shear force. The more sticky or viscous the fluid is, the more force you'll need to keep the top layer moving.
And if the fluid flows easily, like oil or water, it has low viscosity. If it resists more, like glue or ketchup, the viscosity is high. Basically, viscosity decides how chill or grumpy a fluid is when it's asked to move.
Perfect analogy. So Newton's diagram help us see what's happening between two fluid layers. Slow on one side, fast on the other, the resistance in between. It is like teamwork, the little tension. Let's start with the basic equation of Newton's law of viscosity, which is given by tau Ix is equal to minus mu dVx upon dy. This is a mathematical expression of how momentum is transferred through a fluid due to internal friction or resistance. Basically, here tau Yx. Let me tell you what it basically represents. Tau Yx means here subscript x means momentum and y means direction, which can be stated as x momentum in a y direction. We are basically finding x momentum in a y direction by writing tau yx. And for that we use formula minus mu dv x upon dy. Alright, next, let me make it more simpler for you people. Here tau yx is nothing but a shear stress. Shear stress, it is basically force per unit area acting in a x direction on the plane normal to the y direction. You can think of it as much more simpler way. Push the fluid layers are exerting on each other. How much push is fluid layers are exerting on each other. Mu is a dynamic viscosity, a measure of a fluid resistance to the flow. dvx upon dy is nothing but velocity gradient or rate of a shear strain. Sorry. It describes how quickly the velocity is changing between layers in y direction. Okay. In more simpler terms, if you want, I can tell you that the faster the velocity changes from one layer to another, and the more viscous the fluid is, the higher will be the shear stress. The higher value you will be obtaining for tau yx. The negative sign here indicates that momentum is being transferred in opposite direction to the gradient, opposite direction of the velocity gradient. It is resistive force. Now, let's take a more intuitive approach. Imagine you have a two glass plates and there is a layer of honey between them. Honey or any fluid you want of your own choice. It is placed between that two layers of glass plates. You move the top plate while keeping the bottom one stationary. Bottom plate is basically stationary and the top one is a moving plate. The honey near the moving plate also moves faster, and the honey near the stationary plate moves slower. This difference in velocity across the layer creates a velocity gradient. The honey resists the motion due to its internal friction, that's viscosity. Newton said that the force required to move the top plate is proportional to the rate of a change of velocity. It can be given by following formula, which is F upon A is equal to mu into capital V upon capital Y, where capital F stands for force applied, capital A stands for area of the plate, capital V stands for velocity of the plate, and Y is the distance between plates. Again, mu is the proportionality constant, which is nothing but viscosity. Next we are going to talk about units. What are the units of the terms that we are discussing right now? Mu, as you know, it is expressed in SI unit, which is Newton per meter square into second upon meter per second per meter, which is nothing but Pascal per second. Sorry, Pascal second. Or more fundamentally, mu is kg per meter second. That is kilogram per meter second. In CGS system, we use 1 poise is equal to gram per centimeter second. Now for practical purpose, we often use centipoise, denoted by small c capital P. 1 centipoise is equal to 0.01 poise. Here uh, we can use a conversion which can be stated as 1 Pascal second is equal to 10 Pascal equal 1000 centipoise. For reference, you can take water at a room temperature has a viscosity of 1 centipoise or 0.01 Pascal second. So what does viscosity really represent? A high viscosity fluid resists motion. It flows slowly, whether whereas low viscosity fluid like water or air flow more easily. It doesn't resist. It is less resistive, hence flows easily. This concept is essential in many fields: mechanical engineering, chemical engineering, metrology, and even biology. Understanding viscosity helps in designing engines, pipeline, blood flow simulators, and much more. Let's wrap up with some real world applications and a summary. In a real world application, it is used basically in lubrications. Engine oil need right viscosity to reduce wear and tear. Paint and coatings, the right viscosity ensures a smooth application. Medical fluids, blood viscosity affects circulation and is critical in diagnostics. So, summary can be like Newton's law of viscosity relates shear stress to velocity gradient. Viscosity is a measure of fluid's resistance to deformation. Unit SI unit is Pascal second or kg per meter second. CGS unit is poise and centipoise. Conversion 1 Pascal second is equal to 1000 centipoise. And that's everything you need to know about Newton's law of viscosity. And next, we are going to attach a small numerical based on this concept. Hope you will understand it well and will be able to do it properly in upcoming future whenever you will be studying this subject.
So this is the first question in transport phenomena that we are going to solve. So the question is, the Newtonian fluid with a viscosity of 10 centimeters is placed between two large plates. The distance between the plates is 4 mm. The lower plate is pulled in the positive x direction with a force of 0.5 Newton, while the upper plate is pulled in the negative x direction with a force of 2 Newton. Each plate has an area of 2.5 meters square. If the velocity of the lower plate is 0.1 meter per second, calculate the steady state momentum flux, the velocity of the upper plane. So, this problem involves a Newtonian fluid between two parallel plates, where the lower plate moves rightward and the upper plates move leftward due to applied forces. So, our goal is to determine first the steady state momentum flux means tau yx, which is also known as shear stress, and the second the velocity of upper plate v2. The lower plate is moving right, means positive x direction with a velocity of 0.1 meter per second, and the force applied on the lower plate is 0.5 Newton, and the force applied on the upper plate is minus 2 Newton, and this is moving in a negative x direction, and the velocity is unknown, which we have to find. So, the first which we are going to calculate is the momentum flux or the force per unit area, means tau ix, which is also called shear stress, which is equal to force upon area. The y-axis represents the momentum flux in the y direction due to the x velocity component. This component represents the rate of momentum transfer in the y direction due to the motion of fluid in the x direction. Again, cross direction. So, tau yx is equal to force upon area. So, the net force applied on our system is force on the lower plate is 0.5 Newton. Force on the upper plate is minus 2 Newton. So, adding both the forces, we get 0.5 minus 2 upon area is equal to 2.5. We got 1 Pascal second or 1 Newton per meter square. So, now we will calculate the second part, and let us assume that v2 with the velocity of the upper plate. This is the formula of Newton's law of viscosity. After integrating, we get v2 is equal to v1 minus tau ix into y upon mu. Tau ix is shear stress or momentum flux. Capital Y is distance between the plates, and the mu is the viscosity of the given fluid. So, here we got v2 is equal to, after putting all the values which had been given in the question, means v1 is equal to 0.1 meter per second minus tau ix is equal to 1, which we have calculated above, and the capital Y, the distance between the plate, is 4 into 10 to the power minus 3 meter. The mu, the viscosity, is 10 into 10 to the power minus 3. We get v2 is equal to minus 0.3 meter per second. We get the solution of both the question asked, means the momentum flux we get 1 Pascal second, and the velocity of the upper plate we get minus 0.3 meter per second. Now the third one that I have calculated is velocity gradient. The velocity gradient between the plates is related as dvx by dy, means velocity gradient is equal to minus tau yx upon mu, where tau yx is shear stress or momentum flux and mu is viscosity of the given fluid. So, dvx by dy is equal to v2 minus v1 by distance between the two plates, means y, capital Y. So, the v2 which we have calculated is minus 0.3 and the V1 given in the problem is 0.1 meter per second that I have put in the equation, and the distance between them which is given is 4 mm, is 4 into 10 to the power minus 3 meter. After calculating, I got the velocity gradient is equal to minus 100 per second. So we got a negative velocity gradient, which means the velocity decreases in the positive acceleration as we move up, and the upper plate moves in the opposite direction, hence negative x, which matches the applied force delta. This is our final answers. This problem demonstrates momentum transfer in a Newtonian fluid between parallel plates under steady state shear flow. Understanding these principles is essential in fluid mechanics, lubrication, polymer processing, and transport phenomena.